Hello everyone, and thanks for joining this webinar. My name is Yves Gerster, and I'm the Aerospace Industry Manager at Speedgoat. I am excited to talk about electrification testing and certification workflows for aerospace today. Here is what is going to happen today. First, we are going to zoom out and have a look at challenges during aerospace development. Then, we are going to see how those challenges can be met by using real-time testing, and we are also going to have a look at the tools which can be used to meet the challenges. After these rather high-level topics, we will dive into the electrification part with some reference application examples. Finally, we will see how this integrates into the certification workflow, including a demonstration of a flight controller covering the whole toolchain. My goal is to make three things happen in this webinar. First, I want to show you how you can accelerate the development of control systems of electric aircraft with real-time testing and model-based design. Second, you can experience how Speedgoat enables you to streamline certification and testing of aerospace control systems using Simulink, hardware-in-the-loop, and automated testing. Last but not least, you will see how you can seamlessly transition from desktop simulation to real-time testing using only one Simulink model and requirement test suite. The key market trends are clearly towards more electric aviation. This is not limited to electric propulsion systems or VTOL aircraft. Electrification can also be the integration of new, lighter batteries, a more efficient onboard power grid, or more environmental friendly technologies. While purely battery-powered aircraft are restricted in flight range due to limitations on energy density, hydrogen and fuel cell-driven technologies could be the next step for emission-free aviation. In order to become a commercial product, those technologies have to be certified. Since the number of requirements is steadily increasing and the quality expectations of the customers and stakeholders are quite high, new, faster and more reliable ways for testing and certification are required. Given the market trends, let's have a look at the major challenges. Maybe you will find that one or the other has also been bothering you in your development project. Obviously, the flight characteristics are different from modeling a spacecraft to a UAV or VTOL air taxi. However, many of the challenges remain the same. First, there is never enough time. In this competitive market, products have to be ready fast. At the same time, they must be very safe and reliable. Testing failure cases while the aircraft is flying is often not possible. Your aircraft is very likely to contain a battery and the relevant battery management system, which is responsible for battery health charging. Having such a complex product, you want to find as many errors as possible, as early as possible in the design phase in order to save cost during the later design. The challenges of the certification can overlap with the challenges of electrification. Certification can be very time-consuming. Many aerospace standards require code certification. Usually, hardware availability is also a challenge, since certification can't start without the actual hardware. Even after the initial certification of your product is achieved, further changes again have to undergo certification. Real-time testing offers a variety of tools addressing those challenges. Using automated testing, data logging, and tuning of controllers can be automated. Taking advantage of real-time I/O interfaces and communication protocols, automated testing and report generation helps you to save time while maintaining a thorough quality standard. Rapid control prototyping allows you to automatically generate code and to perform bypassing. I will elaborate further on these topics in the next slides. Hardware-in-the-loop testing allows you to verify your code by emulating your plant. You can insert faults and verify the code. Speedgoat offers the off-the-shelf software and hardware for both control design prototyping and control system testing of more electric applications. So, this was an overview of the typical challenges we observe in aerospace development. Before diving into the topic of electrification and certification, I would like to show you the benefits of real-time design and test workflows. What is hardware in the loop, short hill, and how is this linked to real-time simulation and testing? A development workflow has several stages. In aerospace, a development starts with a defined set of requirements. In order to save time, you want to do a desktop simulation of your product or your plant that you're developing. In order to see how your early design behaves in the actual environment, you can leverage controls prototyping. After the successful implementation, you want to test your controller. This can be done using hardware-in-the-loop testing. Since you are working partly on the actual hardware and partly on modeled or simulated components, this part of the development process is called model-based design. You will hear more details about this in a minute. So let's zoom in and have a look at what hardware-in-the-loop actually means. During hill testing, you have hardware under test like an electronic control unit, ECU, or a flight controller. You can simulate the environment of this controller using a plant model. The hardware under test and the plant model emulated by a real-time target machine form a closed loop. Using test automation, you can run many tests in a sequence and verify that all requirements are met. The difference between hill and rapid control prototyping is that in rapid control prototyping, the hardware under test could be your aircraft or Iron Bird. The development task is focused on the design of the controller. This means that the real-time target machine is emulating the controller and executing the code of your embedded control design. What are the benefits of hill testing? Using hill testing, you can test before all the components of your projects are available. You can fix bugs earlier, and corner cases and exceedances can be simulated without damaging the actual hardware. Further components can gradually be integrated. Virtual integration and testing solutions can be leveraged, such as deterministic emulation of plant sensors and actuators. You can use plug-and-play interfacing and leverage the benefits of test automation. To summarize, you can deliver better and faster using embedded software, while reducing costs and risks. With these general workflows in mind, this is a good moment to introduce the systems offered by Speedgoat, which are also used for our application examples. Let's first look at Speedgoat real-time systems to understand what it comprises. Each system is configured to your individual performance and I/O requirements. Changing requirements are not a problem, as you can reconfigure I/O. You can choose from a vast range of I/O connectivity options and exchange them at a later date. All real-time target machines are expressly designed to work with Simulink and Simulink Real-Time. We support the current releases, but we also promise to support further releases. Our hardware quality, our long-term warranty and maintenance services ensure long-term operability of your real-time testing hardware. Delivery of each real-time system includes the real-time target machine, I/O modules configured to your needs, together with accessories such as terminal boards and cables, and the Speedgoat I/O block set for Simulink. The block set library allows for seamless connectivity to the hardware. Speedgoat is supporting all key protocols for the aerospace industry, such as ARINC 429, ARINC 825, AFDX, or MIL standard 1553. Overall, we support over 200 I/O modules. We also have general purpose protocols such as SPI, I2C, Ethernet, and a vast range of analog and digital protocols. You can leverage all relevant I/O protocols at the requested voltage level and sampling rate, and even perform fault insertion. These I/O interfaces can seamlessly be integrated into the workflow from MATLAB and Simulink. In addition to these powerful all-round tools, specific commercial off-the-shelf software functionalities are available. For example, the Aerospace toolbox and the Aerospace block set. Further commercial off-the-shelf software functionalities such as the UAV or the radar toolbox are available. Leveraging this versatile variety of functionalities ensures that all the required tools are provided for your specific project and needs. Now that we've seen the tools available, let's talk about electrification, namely the challenges before jumping into an example of a customer who is developing a hybrid electric aircraft. Real-time testing is especially useful for power management systems and battery management systems. So, more electric aircraft means that not only the propulsion system can be electrified, but other components such as control surfaces actuators, which we saw earlier, can be electrified too. These components depend on a battery and are fed off the onboard electric grid. Therefore, the challenge is to design and test energy and power management systems such as onboard microgrids and battery management systems. For new concepts, the electrification of the aircraft or the integration and testing of a new fuel cell is a challenge. Also, the interfacing with power electronics components and inverters is a demanding task. As mentioned earlier, the seamless workflow integration with Simulink to build, test, and run power systems and power electronics simulations enables you to test power management systems. Using Speedgoat, you can perform battery emulation for up to 320 cells and state of charge and state of health estimations. The hill setup allows you to do signal conditioning. For example, you can increase your voltage level to 28 volts, which is usually required for civil aviation. Also, the low latency interface to power amplifiers gives you a realistic representation of your onboard microgrid. Let's have a look at the example of the FVA-30. The FVA-30 is a hybrid electric aircraft which is under development from the Scientific Aviation Association in Aachen. The goal of this aircraft is to electrically fly the distance between Aachen to Berlin, which is over 500 kilometers. In order to set up an Iron Bird, the association needed a test bench to test the powertrain for the hybrid aircraft. The solution was to use a Speedgoat target machine. They were able to rapidly set up their test bench and start testing. This Iron Bird setup is also an essential part of the compliance demonstration in order to fully certify the aircraft. Let's have a look on how they used the real-time target machine within their test bench. The baseline target machine acts as the controller and heart of the Iron Bird. From the pilot side, input commands such as the throttle and elevator angle are fed into the target machine. Inside the target machine, the actual motor control takes place. On the test bench, the target machine is controlling the motors through the inverters as well as the battery using a CAN interface. Let me quickly show you how they realized the individual components of their test bench. The team used the Real-Time Explorer to keep track of the system state. This is quite useful during development testing. Furthermore, they designed their own GUI in order to monitor and control the tests. The system was modeled using Simulink Real-Time, which enabled them to build a model of their system within a very short time. There are 2 white papers about this topic written by the engineers of the Scientific Association in Aachen, which are uploaded on the Speedgoat webpage. Feel free to have a closer look at how Speedgoat helped them to integrate their BMS system and to perform certification testing. One of the topics related to the example we just saw is the testing of power electronics and electric motor control. One of the challenges is the design and testing of high-fidelity, low-latency power electronics control systems. Another more specific one is the need for powerful hill simulation hardware, allowing for sample steps below 1 microsecond and a pulse width modulation resolution between 10 nanoseconds. By using the Speedgoat system with an FPGA, you can achieve time steps below 1 microsecond and PWM resolution below 10 nanoseconds, even for applications with many I/O channels. So, how can you test your batteries and BMS systems? The typical task would be to monitor or balance cells, to control the state of health or the state of charge, and to do thermal management. Also, inserting faults is a rather large topic. Speedgoat allows you to deploy your SimScape electrical model in real time in order to perform all the tasks mentioned above. The test track can be customized to contain a battery cell emulator, fault insertion units, or even units to perform temperature emulation. Depending on your projects, signal conditioning can be added to the testing solution as required for your needs. Following on from the electrification examples, let's now look at how the same tools can be used for a certification workflow. As mentioned earlier, many aerospace projects at one stage will face a similar challenge, namely certification. Many scenarios need to be tested and documented. Most tests first need to be performed in a virtual development stage due to safety consideration or hardware costs. Also, the test setup must allow gradual integration and testing of line replacement units. The benefit of hill testing using Speedgoat is clearly the test and documentation automation for virtual, hybrid virtual physical and physical prototyping environments such as Ironbird. The modular adaptation of hill systems including I/O interfaces allows you to obtain a solution tailored to your needs. The last great benefit I would like to mention is the seamless workflow integration to run plant simulations designed with Simulink. Most design and verification workflows look similar. There are two main certification workflows used in the aerospace industry. First, there is the more traditional V model, where on the left side you define the requirements and perform system architectures at a higher level. After the development, the software, controller or system is validated and finally certified. You can already see that you can shortcut this process by performing component and system verification before the development of the software is completed using model-based design. The same method can also be applied for more agile workflow like the DevOps one. You can see that the same testing, verification and certification shortcuts can be taken using real-time testing. To summarize, the real-time testing solution integrates well with any overall workflow or design concept. Let's look at another use case: flight dynamics control design and testing, before we dive into the certification example. The big challenge is the need for an environment which allows you to test the behavior of your vehicle, especially during failure cases. You can overcome this challenge by using the environment emulation using the Aerospace block set within Simulink. We have a great example of a flight control system which illustrates that. The aim of this example is to show the testing and verification process of a helicopter flight controller. Although the design of the flight controller has also been done using Simulink, I will not go into too much detail about the development itself. Let me start by showing you the overview of this example. You start off with the requirements for the controls. These can be functional requirements as well as certification requirements. Using Simulink control design, you can prototype the control of the helicopter and already test the basic functionalities using plant modeling. This allows you to create the first virtual twin of your helicopter. With your model and controller, you can simulate signal functions and perform design verification according to design standards. In our case, we use the DO178C. In order to do more extensive and automated testing, you can use Simulink Test, in this case according to the ARP 4754A standard. Once you are happy with your desktop simulation, you can perform the same tests using the actual flight control hardware while interfacing it with a Speedgoat target machine. This allows you to use the same test automation on your real hardware and claim credit for your certification tests. This demo was mainly developed by Bill Potter from MathWorks. You can find the demo using this link or by following the link on the webinar page once we've uploaded the recording. In order to demonstrate this concept, we've done the following. On one Speedgoat target machine, we've loaded the model of the flight control computer, which is our system under test. This target hardware could also be a real flight controller. On a second Speedgoat target machine, we've put the plant model, which is the physical model of the helicopter, the sensors and emulated air data. The two target machines are talking together using an ARINC429 bus as well as an analog DC connection. The analog line is used to send the flight commands to the flight controller, as would be the case in the real helicopter, while the ARINC429 line submits the sensor data such as altitude, attitude or airspeed. This setup allows us to demonstrate the complete test harness. This is the test setup with the joystick for pilot inputs into Simulink Real-Time, which is running on the computer. The target machines are connected through the ARINC and analog bus together and are feeding the information back to Simulink Real-Time and flight gear for visualization. I will now show you the test harness within Simulink before coming back to this complete setup. We start with the desktop simulation part. First, I'd like to show a picture of the actual system under test, which in this case is the flight control computer containing our control algorithms. The flight control computer is surrounded by plant models. For example, for hydraulic actuators, there's 3 of those. The helicopter itself, 3 AHRS sensors, and then there's also pilot inputs, which come basically from a joystick input or pilot stick inputs on that real helicopter. So this represents the system under test. Now, if you want to look at our test manager for this, our test manager file actually is implemented as 3 different tests. So we're doing pitch control, which is one axis. We have small positive steps, small negative steps, and looking at performance roll access control, again positive and negative steps, and then yaw access control, positive and negative steps. So these are the 3 primary axes we're controlling with our control algorithms. They all have performance requirements. These test cases traced to those requirements, which you can see here. In this case, we have the rate tracking performance for the attitude controller. Now, once we run these simulations, which I've already done, and to expedite this, I'm just going to show the test report. We need to have a test report generated as our certification artifact. So this is the report that's generated from Simulink Test. I'll open up here. You can see that all of our test cases actually passed. So we've satisfied all of our requirements. We can also see that within the report itself we have some plots. For example, this is the plot for the pitch axis step. You can see the step response here in the test. You can also see that the test in fact did pass. So here we've done our work on the desktop, and the next step is going to be to transition to the real-time system repeating these same tests. In the project folder, under System Verification, Real-Time Tests, there is a pre-built Simulink test suite comprising multiple real-time test scenarios to test the controller performance for the set point changes into the pitch, roll and yaw direction. The model under test is the helicopter plant, which we can open directly from the test manager. This is the plant model, which is connected to a second real-time target machine using I/O interfaces. Analog signals are used to receive actuator commands from the flight control computer and to send actuator positions and the pilot inputs to the flight control computer. Additionally, the ARINC 429 protocol and respective I/O modules are used to transfer the sensor data from the attitude and heading reference system to the flight controller. So let's take a look at the flight control computer model, which lies in the implementation folder of the project. FCC I/O is the version configured to use the I/O interfaces I mentioned. Here we can see the counterparts of the send and receive block. We receive the analog signals from the actuators and pilot input, as well as the AHRS sensor data over ARINC. The resulting actuator commands are again sent over analog I/O. Going back to the test manager, let's see how we handle the automated initialization of both systems. The preload callback function is used to define the pilot inputs for this test case and map them to the root level import of the model. Then we also build the second Simulink model with the flight control computer and load it onto the second real-time target machine, which is not directly controlled by Simulink test. Before the plant model is executed, we start running the flight controller on the second machine by calling the start command in the pre-start callback function. After our test is completed, we stop the second machine using the cleanup callback function. The outcome of the test is evaluated using custom criteria function. Here we have access to all of the relevant data logs and check that our data meets certain criteria needed to pass the test. The same process is then used to test the step response of the opposite pitch direction, as well as for the other axes, roll and yaw. By executing the entire test suite, all 6 real-time test cases will be run and evaluated in fully automated manner. So let's go ahead and do that by clicking the Run button. We are now running the real-time test. We generated code first. It got downloaded to the target the first time and it's running. You will see that we're sequencing through the 6 test cases. You can see that from the test manager here. It's now completed and the report generation has started. In just a few moments, it will populate the results. This is the report which has been generated. Going back to the test manager, you see all the test results have been populated and all of the tests have passed. To start, we can see the plot of theta, which is the pitch response. And here is the custom criteria that we have set up for verifying the pass-fail for that. Now we can go and have a look at the report. This one is the report for the real-time data. In here, you can see the plot of theta again, which is the pitch axis. Scrolling down through the report, you see the custom criteria showing that we've met the minimum rise time. Here, you can see the negative theta plot. Further down, we have the roll axis and you see the roll step here. So we have a positive roll step. Continuing, we'll see a negative roll step, which is another one of our tests. Then finally, move on down through the report to the yaw step. This one is the step for the yaw rate. You can clearly see overshoot rise time for yaw in the tracking. This signal is more noisy because it is a rate signal, and the rate loops are more noisy than the attitude loops. Here is that same signal back in the test manager view. Finally, down here there are some custom criteria for the test as well. And we do pass the custom criteria. Let's go back to the report summary again. Here's the 6 tests that all passed in the report summary. Moving on, we can now actually look at the 2 reports side by side for the simulation cases as well as the real-time tests. So the simulation case report is on the left. This was what we did earlier on the desktop. The one for real-time testing is on the right. That's also the one that we were just looking at, but here we will be able to actually see some minor differences between the results. There's the pitch step. There is a little bit more noise in the real-time system. This is expected because of the bus delays and the precision of the data used on the target. If we continue in both reports, we'll see the negative step in theta. You can see those 2 plots. They are very close but not exactly the same. We do not expect them to actually be exactly the same for the real-time test versus the simulated. Here is the roll step. You will see there's a little bit of an initialization issue in roll as well in the real-time system. It is compared to the desktop, which is more an ideal situation. Again, here's the negative roll step. You see the basic curve there looks the same, just a little bit more noise on the actual real-time system. And then finally, we can see the yaw rate step. On the right side, there's the positive step. We see the same behavior. There's quite a bit more noise on the signal, but basically the overall shape is the same. And there's the negative step too. On the right side, you see more noise on the yaw rate. For the engineers, this could mean that there could be some work to do in order to damp out some of the noise in the real system. They could maybe take into account some extra delays that are actually in the system due to the digital bus feedback, for example. Now we can go back to the report summaries. And these 2 reports actually now provide us with the certification evidence we need to show that we fully tested the system. Now, instead of running the automated test, we can also perform real-time testing using manual pilot inputs. This can be useful during the development testing or by determining handling qualities. So now we give a manual input to the flight controller and see how the plant reacts. You can see some movements on the gauges on the screen. They are moving as we give different pilot input signals. In this case, the visualization of the helicopter is done in flight gear, since Simulink provides a direct output of flight data such as attitude, RPM or airspeed to flight gear. After having seen this demo, I would like to show you the example of how Airbus used bypassing to accelerate their certification process. The challenge that Airbus was facing was to tune different functions of their aircraft and flight control systems. If every parameter change has to go through a review and test process, such a tuning exercise can take months. Therefore, some smart engineers at Airbus introduced the bypassing rapid prototyping. This allows them to tune parameters while having their Ironbird running by bypassing single functions. I will show in the next slide how this is done. While data gathered with this method is not used for certification directly, Airbus used bypassing to speed up the process leading up to certification. At the end, all requirements are proven on the real computers or on the official certified platform OCASIM. As you can see, Airbus used this method on many of their projects for multiple tasks. For example, they tuned the flight control functions on the A380 or tuned the pitch control law on the degraded flight controls on the A330neo. Furthermore, they used it to monitor actuator failures for their long-range fleet. For the single-aisle program, Airbus used the Speedgoat target machine to test the flare law, which controls the critical landing phase. I would like to show you how bypassing actually works. If you want to work on one specific function for a new software built on your flight controller, which is already certified, this may come in handy. Let's say you have your flight controller here. With your flight control software, which is represented by these blocks which run in a continuous loop, your goal now is to certify just one function or test and tune one function. Using your rapid control prototyping system, which is obviously a Speedgoat target machine, you can input the variables from the flight controllers or from the flight control software into your Speedgoat target machine, perform one specific operation, and then output the variable again. This allows you to tune only specific details of the algorithm. As you saw earlier, hardware in the loop is usually preceded by rapid control prototyping. Your workflow may deviate slightly, but I am pretty sure that you agree on the following three main motivations for real-time based control prototyping. By testing early, you can prove that your algorithms work in real-world dynamics. You might find better trade-offs and tweak performances. The unified workflow provides a path from desktop simulation to automated testing with flexible and powerful hardware. This unique combination allows you to vary less while testing. Ultimately, you can be more innovative, expose design flaws earlier, and shorten time to market. How can companies integrate model-based design in their electrification and certification workflow? It is important to know that implementing this new approach may not be straightforward at first. Creating models will take some time and also requires new skills. So, there is an initial investment for every company planning to implement that. Many aerospace companies work under a lot of pressure to achieve certification and sometimes don't take the time for the implementation of better workflows. They are often punished later on. So, it is a good idea to start this early. This example from Airbus showed how they overcame their initial fear of the new approach by pointing out the benefits. Alonso Pardo presented this graph at a MATLAB symposium. I find it quite interesting because it shows how you can increase the flexibility and increase reusability using model-based design. Finally, the engineers can detect design failures earlier and also simply be engineers again. So they can spend time understanding the systems and don't have to spend time building up the models and worrying about interfaces or documentation. To conclude, I hope that you learned how you can accelerate the development of control systems of electric aircraft with real-time testing and model-based design. Second, you experienced how Speedgoat enables you to streamline certification and testing of aerospace control systems using Simulink, hardware-in-the-loop, and automated testing. Last but not least, you saw how you can seamlessly transition from desktop simulation to real-time testing using only one Simulink model and requirement test suite. Thanks for staying with us until the end of this webinar. For more information, just visit our website speedgoat.com.
You want to learn more about real-time controls testing? Then find additional content linked here.